Contingency tables is a way of showing the information in a two-way table in a way that may be more useful for the reader to have a look at. So this first table where we have all the numbers in there, this is a one-way table. Correction, two-way table. This is a two-way table. So a contingency table will look the same as that, but it'll have percentages. There's three different types of contingency tables that we can make. The first one, we can calculate the percentages per table. So the whole table will have a total of 100%, and then each of these individual cells, I'll calculate the percentage of the total. So the percentage of gym users, male gym users in the class, was 2 on 15 converted into a percentage, so 13.33%. And then I'll go ahead and do that for every other cell in the table. And now that I have the table in that form, I can answer the sort of question like, what is the percentage of male gym users in the class? Since I have the total class and that my total I'm after here is class, I can just read off my graph this 13.33%. Okay, so that's where I can read it off from. I can also change my contingency table so that it's by row instead of by table. So what this means is my goal is to have 100% in my rows, and the way I'll achieve that is by on each row. So for example, in this first row, I'll have 2 male gym users divided by 7 gym users total, and that's what'll go in this cell. Okay, so I'll get my 28.57%. And in the next row, for females, it'll be 1 female gym user divided by 8. And I'll do that looking horizontally through the table at all times, and be able to fill in my table like that. And now that I have it in percentages per row, I can answer this sort of question like, what percentage of males use the gym? And I can just read off the answer directly. So of all the 100% males that use the gym, 28.5% of those are male. So I can just read off the answer there. Finally, calculating percentages per column. That means each of these columns, the total needs to be 100%. And looking back at my table at the top, I'm using 3 as my 100%, so it'll be 2/3 converted into a percentage. Yeah, just looking at that 2/3 as a percentage. And I'll obviously do the same thing for all these other cells as well. Again, now that it's in this form, let's see what we can do with it. Find the probability that a randomly selected gym user is male. Well, looking at all the gym users, how many of these are male? Okay, the 66.66%, which we can just read off the graph. Correction, off the table. Okay, so you got 3 options. You don't know which one's going to be more useful until you make it and see what's more useful for the user, for them to read information off. There is another use of contingency tables, which is looking at the percentage of people that suffer from a certain illness and the likelihood that the test for that illness will be correct. So I'll have a look at this example. About 2% of people suffer from diabetes, and the blood test for diabetes is 99% accurate. So we can set up this contingency table for the test results and the disease presence. So sometimes it's important to know how often are we telling people the wrong thing? How often are we telling people they're diabetic when they're not actually diabetic, for example? So let's have a look at this table. Let's try and put in the information we know. It says about 2% of people suffer from diabetes. So that means in the population, 2% are diabetic. So 98% are not diabetic, giving us a total of 100%. I need to put totals in here. Okay, now here's the interesting part. Let's see what happens when these people get tested. So the test is 99% accurate, which means that when these 2% of people that have diabetes get tested, 99% of those will be told that they have diabetes. Okay, a positive test. Positive says, yes, you have diabetes. So in this cell here, I'm going to find what 99% of 2% is. So the percentage of the people with diabetes that correctly get told they have diabetes. So it'd be 0.99 times 2%, which would be 1.98% of the population that gets tested. I can then subtract that from my total and find that in here is 0.02%. In a similar way with the ones that aren't diabetic, there's 98% of those. Okay, in here, 99% of these, 98% of the population will be correctly told that they're not diabetic. So 97.02% of the population. Again, can do some calculations to find that one in the middle. Okay, and then I can add horizontally as well. So what this means, probably the most important cell, just looking at this table, is probably this one, which is telling us that even though only 2% of the population have diabetes, about 3% of them will be told that they have it when they go to the doctor to get the blood test. So let's have a look at part B and part C. So find the probability that a positive result is false. Okay, well, let's have a look at all these positive results. So I'm focusing just on that row in the table. So my total is the 2.96% of the population who get told they have diabetes. The probability that it's false is that they're being told the wrong thing. Okay, so that would be the people, the 0.98%, who are told they have diabetes when they actually don't. And we can convert that into a percentage. So about a third is the likelihood of being given bad news when you don't actually have that disease. Okay, and the last question, find the probability that a negative result is false. Well, we could do this exactly the same way as part B by just looking at the second row of results, or we could convert into a contingency table by rows, which might be more interesting. Okay, so converting it to a contingency table by rows, I'd have 100% horizontally with my totals here. And even though my top table is all full of percentages, I'll still do the same thing. So in here would be my 1.98 from here, divided by its horizontal total of 2.96, converted into a percentage. So I'll go ahead and do that for all those cells. And then looking for the probability that a negative result is false. I'm looking at all these negative results, and a false result would be telling someone they don't have diabetes when they actually do. And I could read that result off the table and I wouldn't have to do the calculations. So it might be more useful to present information in that way. Alright, so from here, have a go at those textbook questions.